Swayam Prabha. Digital India. Educated India.
Okay, fine. Yeah. So, what I want to explain to you is to go through the process of how we calculate the transition probability of a molecule undergoing a spectroscopic transition. Now, when you say molecule interacts with the electromagnetic field, remember, electromagnetic field is electric field and magnetic field oscillating perpendicular to each other and oscillating in time. So the electric field, for example, in time, which is oscillating, is a magnitude E0 times cosine omega t. This then is the direction of the oscillation. So if the molecule is oscillating like this is the direction of the oscillation. Okay. Now the magnetic field will oscillate perpendicular to that, and they both oscillate in direction, and this is the propagation. The electric field will propagate like this. The electric field oscillation is given by this formula, E0 cosine omega t. What is omega? Omega is the radiation frequency. That is the frequency of the electromagnetic radiation. 2 pi times nu. Omega is the angular frequency. So the linear frequency is 2 pi nu, so its nu is omega by 2 pi. So the electric field is oscillating that frequency. Now, it must interact with the electric property in the molecule. Otherwise, there is no energy transfer. There is no resonance between something that the molecule is changing and something that the radiation is changing. So this is one oscillator. This is another oscillator, molecular property. And if they both oscillate at the same frequency, it's possible for the energy to flow from one direction to the other, which is what we call this resonance between the molecule. What property of the molecule oscillates? It's the electric dipole moment. Okay? Molecular dipole moment oscillates. Suppose the molecule is rotating like this, and if the dipole moment is in this direction, there is no oscillation. But if the molecule is rotating like this, and the dipole moment is in this direction, it is also rotating like that. Okay? So, rotational motion can change the dipole moment, oscillate the dipole moment. That's a rotational motion. Now, if the molecule is vibrating, the dipole moment is increasing or decreasing if it is in this direction. Okay? Therefore, the dipole moment will also be changing. It's the frequency of the change in the dipole. That frequency must match with the radiation frequency. Then radiation is absorbed by the dipole, causing the molecule to go from lower energy to the higher energy. So the interaction between electromagnetic radiation and the molecule in the optical spectroscopy is the interaction between the electric field of the radiation and the electric dipole moment. Okay? Now, that energy, interaction energy, ET, is the dipole moment minus U, not the electric field vector, scalar. This is a vector product, scalar product. Okay? Therefore, if the ET is in the Z direction, then mu naught ET will be in Z. Okay? So you can see that if mu is given by Z component of mu, and ET is E0 cosine omega t Z, then this energy minus mu dot ET is minus E0 cosine omega t times mu Z. This is what we call as the Hamiltonian or interaction of radiation with the molecule. The Hamiltonian, it's quantum mechanical because the dipole moment, the molecule, is a quantum mechanical quantity. It's an operator. Molecular property, which is quantum mechanical, is the dipole. Dipole moment is a quantum operator. Therefore, this is an operator, H1T, the energy of the dipole interacting with the external is a Hamiltonian. This is time-dependent Hamiltonian. Okay. This time-dependent Hamiltonian is there as long as the electric field is there. If you turn off the radiation, then the molecule, the dipole does not emit further interaction energy. The molecule will evolve according to its own Hamiltonian. Molecule has a Hamiltonian because atoms are moving along, electrons are moving, and atoms will have potential energies between them. Therefore, you have the kinetic energy of the molecule, like in the hydrogen atom case, there is the kinetic energy of the proton, that's the kinetic energy of the electron, and you neglect the proton kinetic energy by saying proton is very heavy, the electron kinetic energy. And then the potential energy is the energy between the positive proton and the negative electron, the Coulombic force. And you solve the hydrogen atom problem. And you get the energy levels, like the S orbital, P orbital, D orbital, and so on. So each molecule is characterized by its own Hamiltonian. It's time independent, stationary. But the moment the radiation is on, the molecule is now undergoing time-dependent interactions. And the time-dependent interaction is called H of T. This H of T is nothing other than the molecular Hamiltonian has its own kinetic energy and potential energy. That's called H naught. And H naught can be solved using time-independent Schrodinger equation. So if there are two states for the molecule that we think about, then those two states can be called eigenstates of the molecule. You remember last time we drew two energy levels. Those two energy levels are the two states, psi 0 and psi 1, with the energy E0 and E1. So here is it is. So the molecular Hamiltonian has an eigenfunction called psi 0 and an eigenfunction called psi 1 with the corresponding energies E0 and E1. And obviously E0 is not equal to E1. Okay. And the wave functions psi 0 and psi 1 are orthogonal. See that psi 0 star psi 1. This detail. This is 0. Okay. This integral is 0. So because these are eigenfunctions corresponding to different eigenvalues, they are orthogonal to each other. The eigenfunctions are also normalized so that you can see that this is psi 0 star. This is psi 1 star psi 1. That is also 1. So you can see that the eigenstates of 0 are, that is this Hamiltonian, time-independent molecular Hamiltonian, added to the time-dependent Hamiltonian H1. So the total Hamiltonian is what is here. H of T is the sum of the H naught and H1. This is the wave function we want to find out. This is the solution that we are looking at. I H bar D psi by dt is Ht psi dt. Now, if the radiation is absent, then the solution psi of t is either this one, psi naught, or psi 1, or some linear combination of the two. Okay? But now there is a time-dependent interaction due to the presence of radiation. Therefore, the wave function is different. We need to find out that wave function. So, spectroscopic problems usually look at the solution of the Schrodinger equation according to the time and some approximation methods. This cannot be solved exactly. You need to do approximation methods. And details of those things, I would not go now, but I will give you what the answer is. As you learn more and more mathematics and more physics in the year coming, you will see that these things, these solutions are something that you can do yourself. So let me simply say the first thing, that let us solve the Schrodinger equation, this one, without the H1. H1 is, that is, this radiation. Let's assume that. Please remember, time-dependent equation. You have solved H naught psi is equal to E psi. H naught psi is equal to E psi. That is a time-independent solution. You want to solve time-dependent equation without the H1. And then with the H1. With the H1, you get spectroscopy. Without the H1, you get molecular states evolving in time due to their own harmonic. So if you solve this equation, for example, IH bar d psi by d is equal to H naught psi, or psi naught and psi 1, you see what you will get. So the solution you will get for psi of t is exponential minus IH naught t by H bar psi of 0. That is, some for initial state psi of 0. The wave function at some other time is given by the evolution operator. This is called the evolution operator. E to the minus I H naught. This is the molecular output. So the wave function is always time dependent. Always. Except that the probabilities which are calculated using psi star psi can be time dependent or time independent, depending on whether the Hamiltonian is time dependent or time independent. The wave function always has this solution, even for zero order Hamiltonian. Okay? That is H0, which is there. So there are two eigenstates. These psi zeros are two solutions. This one. Psi 0 is the solution psi 0 I wrote to you earlier, and psi 1 I wrote earlier. So if I substitute that, then you see that there are two time-dependent solutions, depending on what we put here, whether we put this psi 0 or whether we put this psi 1. Because H naught acting on psi 0 will give you E naught. H naught acting on psi 1 will give you E1. Therefore, you see these are two different solutions. So what are those two different solutions? Those are these two solutions. Psi naught of t is E to the minus I. H naught on psi 0 is E0 t by H bar times psi 0. Psi 1 of t is, if I put this other eigenfunction for H naught with the eigenvalue E1, the way psi 1 t by H bar psi 1. Now, you only know that H naught psi naught is E naught psi naught. So how does the exponential give you that answer? Exponential waves. You see that the exponential is nothing other than 1 minus, exponential of minus x is 1 minus x plus minus x whole square by 2 factorial plus minus x whole cube by 3 factorial. If you put that expansion and if you apply H naught on psi naught, you get E naught psi naught. If you apply H naught square on psi naught, you will get E naught square on psi. So you will get this expression 1 minus I E naught t by H1. Thus H naught is replaced by E naught acting on psi naught. So exponentially you will get the same answer e to the minus I E naught t by H1 psi naught. That's what goes through. That is this. The same thing you do for psi naught. Now, these two are in the absence of radiation. These two are only with the H naught, which is the molecular Hamiltonian, not with the radiation. With the radiation, we don't know the solution. Therefore, we have two basis functions. The solution in the absence of radiation for the two energy levels evolving in time by these two factors. Make psi 0 and the psi 1, these two. Therefore, we propose in the presence of radiation, most important thing, now you see that, the radiation field is added here in the Hamiltonian, H1 of t, this one. Yeah. So you see that the original wave equation now has become a new wave function because of this H1t, and the new wave function is, on a trial basis, is written as the linear combination of the two eigenfunctions, psi naught e to the minus I naught, this one, the psi naught of t, and the psi 1 of t. So there are two basis functions. Its general solution psi is written as a linear combination of these two solutions with two constants, a0 and a1. But because this is a time-dependent Schrodinger equation, this a0 and a1 are also time-dependent. They also depend on t. If you recall in your digital hydrogen solution, superposition, linear superposition of wave functions, you can do with constants. Here, the constants will depend on time. So we propose molecular Hamiltonian eigenfunction in the presence of the radiation, that is psi, these two ones. The presence of radiation is nothing but the linear combination of the two evolving basis states with coefficients a0 and a1. So we need to find out a0 and a1. If we know, then we know the answer. Okay? The only thing we know is that a0 and a1 have a normalization property. But we don't know exactly what is a0 and a1. So what we do is substitute this equation, okay, this one, in the differential equation here. This is a proposed solution with two unknowns, a0 and a1. Therefore, we want to determine a0, substituting it in here and taking the derivative, d by dt. If you take the derivative, you see that there is a0 is also time dependent. This is also time dependent. a1 is time dependent. And this also is time dependent. You see that e to the minus i1t. Therefore, when you take the derivative with respect to psi of t, you get many terms. And here, you will get h0 on psi of t, if you look at that. h0 on psi naught will be v0. h0 on psi 1 will be v0. But then you don't know what h1 of t does. So now this is a complex differential equation that needs to be solved. I'm not going to solve that here. I'm going to give you the answer. Solving this equation is the first step in molecular spectroscopy to understand the rigorous of spectroscopy. Therefore, all of you should spend time in the coming year on how to solve this particular equation and how it can be answered. The solution is already there. I will show you the textbook at the end of the lecture. Okay, at the end of this lecture. It's all solved, except that you must understand how to do this mathematics. Using approximation limits, the mathematics is completely removed, but it's very beautifully explained in a textbook that I use for spectroscopy course. And the textbook is something that what we should have access to. It's by a very famous Canadian spectroscopist, and I have enjoyed reading that often. So, the solution can be obtained for the differential equation using approximations. The approximation is known as rotating wave approximation. You can find out a0 and a1 by a complex formula. Now let's explain this formula. Okay. This formula says a0 of t is cosine sum omega t minus I, this is square root of minus 1. It's a complex imaginary. By delta by omega, sine omega t by 2, e to the minus I delta t by 2. And a1 of t is I, a factor called omega r. It is known as Rabi frequency, II Rabi frequency. divided by the same omega sine omega t. This is cosine omega t, and this is sine omega t e to the minus I delta t by 2. Now, what is the notation here? First of all, you remember H1 of t. Dipole interacting with the electromagnetic field. Okay, that's the mu z E naught cosine omega. We remember that. This is the first H mu. And also, H nu is the difference between the two energy levels, E1 and E0, which we call as H bar omega naught. Okay? And this is the basic resonance energy difference in the two energy levels. But the radiation is, remember, has a frequency omega, not omega naught. It's very close to omega naught. If it is exactly omega naught, the resonance will happen. But if it is omega naught plus minus some small value, that is around omega, the difference between the two, omega and omega naught, okay, is delta. At resonance, delta is 0. But slightly away from resonance, delta is not 0. That delta is what appears here. You see that delta here, and this delta here. That's the delta. And what is the Rabi frequency omega r? Omega r is related to our dipole strength. You see that mu z and E naught, the electromagnetic field, divided by H bar. H bar is H by 2 pi. That's constant. So the Rabi frequency omega r, in honor of a very famous physicist and Nobel laureate who discovered the molecular beam resonance in the 1930s, more than 100, almost 100 years ago. He was at Columbia, very famous physicist, and in honor of his and his contributions, this frequency is known as Rabi frequency, and it's nothing other than the strength of the dipole and the strength of the electromagnetic field, E naught, H bar. So with this notation, you can see that if there is a resonance, what is resonance? Resonance is omega is equal to omega naught, which means delta is 0. If delta is 0, please remember this is e to the 0. E to the 0 is 1. Then the delta is 0, therefore this term is 0. Okay? And only one more thing that you need to know, what is omega? This omega. Omega is in the next slide. Is the Rabi frequency square plus the delta square root. So if delta is 0, this omega is nothing but the Rabi frequency. Now you see why it is important. Okay? Why that number is important. You see it. When delta is 0, this is 1, this is 0, and this becomes omega r because the other delta square is 0. Therefore, A naught of t is cosine omega r t by 2. A1 of t, this is omega r. Please remember this omega is omega r. Therefore, this is 1. So here it is I sine omega t, which is omega r. This is 1. Exponential of 0 is 1. Okay? That's what we will see in the next slide. A naught of t is cosine omega r t. A1 of t is I sine omega r of t. So what does this tell? A naught and A1. Please remember A naught square, if you look at it in the wave function, original wave function, it has the lower energy right hand. A1 contains the higher energy contribution. So A naught square means probability that the system is in the lower energy. A1 square is the probability that the system is in higher energy. And now you see A naught and A1 oscillate with sine and cosine formulas. Therefore, where cosine is maximum, sine is 0. Where sine is maximum, cosine is 0. Okay? Therefore, the population oscillates between maximum ground state and the maximum sine state by the frequency, and the oscillation frequency is the Rabi frequency, omega r. That's what omega r. So, but if it's slightly off resonance, e to the I delta t, those things are not zero. And when delta is not zero, you see that there is a more extended solution. The square, absolute square of A1t becomes omega r by omega square sine square. Easy to see that here. When delta is, let me see. Yeah, A1 square. We are only looking at A1 square. A1 square, the delta is very small, slightly off resonance. Omega is not equal to omega naught. This one. This is non-zero. So when this is non-zero, you see that there is a small delta t. But if you take the absolute square, you see I into minus I will become 1 because you need to multiply this by its complex conjugate. So I will become, you multiply this with a minus I, and exponential minus I delta t by 2 multiplied by exponential plus I delta. That's the absolute square. So the exponential will go away. I will go away. What you will be left with is omega r by omega whole square, which is this. Square. So A1t square, that is the probability that the system is in the excited state, is sine square. Therefore, it oscillates like a sine square function with time. There's no decay. The system either is in the excited state or is in the ground state. And at t is equal to 0, it is in the ground state because sine is 0. There is no A1, only A0, which means everything is in the ground state. Otherwise, it oscillates to the excited state and then comes back, oscillates and comes back, oscillates and comes back. Now, that oscillation depends on the ratio of omega r to omega r. What is omega r? Omega r is, of course, clearly known to you. It's the dipole moment multiplied by the external magnetic field divided by h bar. It's fixed by the molecule, fixed by the electric field. So that remains fixed. Now, suppose this omega, which is the square root here of omega square plus delta square. If this omega is different from omega 1, you see that it oscillates with a different frequency. Doesn't oscillate the Rabi frequency. It's different. So how does the whole thing look like? Beautifully done in the next graph that you can see here. So if you look at the wave function that we proposed that as A0 times psi naught times this one. So A0 square gives you the probability that the system is in the lower energy, and A1 square is the probability that the system is in the higher energy. And now you can see that the ratio psi of t square, if you look at it, is A0 square. It's the constant. So if you plot A1 square as a function of t, you can see when delta is 0, that is the resonance, it's a huge oscillation, amplitude oscillation. You see two oscillations. But if delta is not 0, but delta is slightly away from 0, so let's make delta equal to omega r, then you see that the oscillations are smaller amplitude. See that. If this one, so smaller graph, delta is far away from the omega, 3 times omega, then you can see that. So the physics is very clear, and the chemistry is also very clear, that if the frequency of radiation is exactly the same as the gap, omega equal to omega r, omega naught, then the system oscillates hugely, 0, 1, 1 to 0, 0 to 1, 1 to 0, keeps oscillating. That's a large graph here. But if the radiation frequency is far away from the energy gap, then the system doesn't absorb off resonance. It doesn't absorb. And the farther away it is, the smallest probability that it will go to the excited state. A1 square is very small. You see the star graph. A1 square is very small. It's still oscillating, but it's very small oscillation. So, therefore, it is very important that the radiation is chosen as close to the gap between the two energy levels for absorption to take place, for resonance to take place, and that is shown by quantum mechanics. It's a very fundamental relation. I didn't show you the mathematics, but I showed you the results. And I showed you what the understanding is. Now, one last thing before I just wind up lecture. So now you can see. You can see that the transition probability is A1T squared because that connects the higher energy state. And from E0 to E1, it decreases drastically as the light frequency becomes very different from the resonance frequency omega naught. Therefore, excitation does not happen if the mismatch between omega and omega naught is very high. There is no mismatch, maximum excitation. Molecules go up and come down with very large amplitude. The final component is what is the intensity of this transition. You saw that there is a benzene spectrum in the last lecture. You saw that different lines have different heights, different intensities. How is the intensity coming with the dipole moment of the molecule? This is an affiliation. This is a fixed formula. Okay? Again, I did not derive you the formula. The formula gives you intensity in terms of the constants and in terms of the frequency of the light, okay, nu, as a constant multiplied by 1 minus exponential h nu by kt is exponential of minus the initial state. EA is the initial state of the system divided by the total number of molecules in the volume, total n naught plus n1. And then there is a quantity called the partition function, Z of t, which is involved. These are all numbers. But the most important quantity is this one, R, multiplying all of this. This R is nothing but the matrix element of the dipole moment between the initial state and the final state. This is called the oscillator strength. The absolute square of the matrix. This square bracket, this bracket, angular bracket, is known as the Dirac-Bra kind of formula. But this is nothing other than integral of psi 1 t star uz psi naught t d tau whole square. That's what this is. And you can see that this matrix element, absolute square, connects the initial state to the final state through the dipole moment operator. And this absolute square matrix element is intensity is proportional to the absolute square of this matrix element. And there is a delta factor which I did not include. The delta tells you that the energy gap mu is the same as the resonance radiation energy h nu. So this is the final formula which tells you two things in spectroscopy. One, that the quantum mechanics of the time-dependent radiation is a complex problem, but it is important that the transition problem results. And the second is that the intensity of the transition is proportional to the absolute square of the matrix element of the initial state connected by the dipole moment, mu. This is the initial state, psi naught t, connected by the dipole moment to the final state. And this matrix element, absolute square, is giving you the strength of the intensity in addition to other factors. These are two fundamental principles of spectroscopy. Same everywhere, whether you do vibration, whether you do rotation, whether you do electronic transition, whether you do X-ray, It's not matter. These rules are fundamental to the whole of spectroscopy, and they constitute the basic principles that the dipole moment of the molecule is important, either a permanent dipole moment or a changing dipole moment. It's important in connecting the spectral molecule to a spectrum absorption energy of the radiation in the spectrum. And it's a square of the absolute square of the matrix element, which is proportional to the intensity. These two are very well known as the basic principles of spectroscopy. And I will stop here with these two, because the rest of it is application of these two to specific systems like infrared, to Raman spectroscopy, to microwave spectroscopy, even to NMR spectroscopy, and so on. We will see these things one at a time by different practices, teaching you different aspects of it. Okay, so let me stop here, and I hope if you haven't seen this, this is the first clear and important result that you should remember, and then you should try to also write this during your year of MSc that will spend for 1 more. Okay, so let me stop here. If there are any questions, I'll be happy. I'm sending you the problems by email to several person and to Mr. Arun, so that you'll be able to look at them, and you have the remaining 10 days to solve. Okay? Thank you. Thank you.
Swayam Prabha, Digital India, Educated India.